This is another problem that involves pulleys and Newton's law. And what we have here is a pulley system where A is moving to the right at a speed of 2 meters per second. We're asked to figure out what the velocity of A is after it has moved 4 feet. So when it has moved from here to here, which is 4 feet, and what is the tension in this cable, and what is the acceleration of B. So in order to figure this out, the first thing we have to do is we have to dimension our pulley system appropriately so we can figure out the acceleration relationship between A and B. And to do that, we dimension the length of the rope that moves, and we're going to call this length, this blue length, S sub A, and we are going to call this length right here S sub B. And we don't need to take this part of the rope into consideration because this rope does not change with respect to time and it's just constant. If you had taken it into consideration, you would call this length of the rope from here to here in H, and this H would be a constant and come out of the equation. So if so what we know from our dimension, we're going to take X is to the left, which is positive, and Y is down, which is positive. And we know this because we're dimensioning from our datum point this way. And this becomes important when we use Newton's laws. So if we trace the length of the rope, we have a length of SA plus SB plus SB. So we have plus 2SB is equal to some length of rope. So if we differentiate with respect to time, we get the velocity of A plus 2 times the velocity of B is equal to 0. And this L, which is a constant length of rope, becomes a 0 because any constant that's differentiated is a 0. And if we differentiate again with respect to time, we get the acceleration of A plus 2 times the acceleration of B is equal to 0. And this is the relationship between the acceleration of these two blocks. So now we can go back and we can look at the free body diagrams of these blocks. And let's look at block A first. And with block A, we have this block right here. It's going to have a weight coming down, and this weight is 10 pounds. And it's going to have a force that is coming up, and this force is a normal force because it is on this surface, and the surface exerts a normal force back onto the block. So this is block A, and we'll just call it NA. Now the other two forces we have a tension force with this rope right here, and we will call this T. And we have a force because we're given information about friction. The coefficient of kinetic friction is 0.2. So it's moving to the right. Friction opposes motion. So the force of friction is mu k times n sub A. And now we have to draw our kinetic diagram. And to draw this, we have block A again, and we are going to assume that the A has an acceleration in the positive direction, and we've defined the positive direction to the left, and it has a mass of 10 divided by g. And let's just make this a little clearer. The mass is 10 divided by g, and g is equal to 32.2 feet per second squared because we're in English units, and acceleration of A is to the right, to the left, which is positive. Now, if we look at the free body diagram of block B, this is block B. It has a weight that is coming down, and this weight is 20 pounds. And it also has a force of 2T, which is coming up because this rope is split into two parts. So it is 2T. If you can analytically, you can just sort of see that by looking at this diagram, but if you want to prove it, and you say, well, how do you know that's 2T? If we look at this pulley right here, and this is the pulley of B, so we have two forces. We have a rope, let's call this tension of B, going down, and we have these two ropes going up. So we have T here and T here. Now, one of the assumptions we make with pulley systems are that they're massless. So we have the sum of the forces in the y direction is equal to a mass times an acceleration in the y direction. Yes, this pulley is accelerating at the same rate as B. However, its mass is 0. So because its mass is 0, the sum of the forces in the y is equal to 0. And if we sum our forces up, positive down, we have TB minus 2T is equal to 0. So this TB is equal to 2T. And this TB is just this little string I'm calling right here. So that is why this force going up is 2T. But you might be able just to look at this problem and notice there's no other forces going on this pulley. So the force that B sees right here is the same as 2T. But this is Y. Okay. So now we have 2T and we have 20 pounds. And if we look at the kinetic diagram of this, we're going to have a mass. This is B, a mass which is 20 divided by G times an acceleration. And we are going to assume a positive acceleration. So we're going to assume down. And if we're wrong with either of these assumptions, a negative sign will fix it when we solve for AA and AB. The negative sign will tell us, nope, you're actually wrong. The acceleration is going in the other direction. So when we sum our forces up, let's sum our forces in A up. The forces in the Y direction, and it's equal to a mass times an acceleration in the Y direction. This is BA. We know that our forces is 10, so 10 minus NA, and we know there's no acceleration of this in the y direction. There's no acceleration in the y direction, so this is going to be equal to 0, and we get our normal force is equal to 10 pounds. And this is going to help us out when we sum our forces in the x direction. When we sum our forces in the x direction, it's equal to a mass times an acceleration in the x direction. We have this minus t because it's going to the right against what we called positive. So we have a minus t plus this mu k times na is equal to a mass, which is 10 divided by g, times this acceleration in the a direction. And we do know this number. We know that mu k is 0.2 times 10. So if we fill that in, we have minus t plus 0.2 times 10 equals 10 over g acceleration of a. Now we can look at the block B, and in this block we only have to consider the y direction. There's nothing happening in the x direction. So the sum of the forces in the y direction is equal to a mass times an acceleration in the y direction. Our sum of the forces, we have a 20 minus 2t is equal to this 20 over g times the acceleration of b. And now we can use these three equations right here, our first equation, our second equation, and our third equation, to solve for variables and substitute them into these other equations to figure out this tension, this acceleration of B, and we're going to also need an acceleration of A. So in order to do this, let's begin. If we solve this third equation for t, we get t is equal to 1/2 times 20 minus 20 over g times AB. And now we can solve this equation for AB. AB is going to be equal to minus A, the acceleration of A, divided by 2. And we can now substitute this acceleration of A into this equation, and we get t is equal to 1/2 times 20 plus 20 over 2g times A sub A. And this is negative sign right here is why this became a positive sign. So we have this expression for tension, and we can substitute that into this second equation right here. And when we do, we get minus 1/2 times 20 plus 20 over 2g times A sub A. This right now is just this expression for t, plus 2. This 10 times 0.2 is just 2, is equal to 10 divided by g times A. And we can now solve for AA. We only have one variable, and the acceleration of A is going to be equal to minus 17.17 feet per second squared. And what does this mean? This minus sign means that the acceleration of A, our assumption was wrong, and the acceleration of A is actually to the right. It is moving towards the right, not to the left as we had initially guessed. But that's okay. We can also figure out the acceleration of B. The acceleration of B is going to be equal to the minus the acceleration of A, which is minus 17.7 divided by 2, and this is equal to 8.58 feet per second squared. And this tells us that the acceleration of B is actually down. So the acceleration of A is actually this way, while the acceleration of B is actually down. And we can take either one of these equations, plug them into this second or third equation, and we can get what tension is. And if we plug it in for tension, we get a tension is equal to tension is equal to 1/2 times 20 minus 20 over g times the acceleration of B, which is 8.58, and this is equal to 7.33 pounds. And this is what the tension in this rope is. Now, the question is asking, A is moving to the right, what is the velocity of A after it has moved 4 feet? If we take a look back at our kinematic equations, we have this equation right here. A final velocity squared is equal to an initial velocity squared plus 2 times the acceleration times some change in x. And we know what this change in x is. Since it's moving to the right, this change of x is minus 4 feet. We get minus 4 because if we say it starts at 0, 0, and it's moving to the right, it's moving in an opposite of our positive direction. It's moving in our negative direction. So x is going to be equal to minus 4. Our acceleration of A, we already found out, is minus 17.17. and there's a 2 in front of it, and we know we have an initial velocity of 2 meters per second. 2 meters per second. So this is what our final velocity is going to be equal to, our final velocity squared. And when we do this out, we have the final velocity is equal to 11.89 feet per second. So this is how fast this block is moving. Now, you could say that you have to remember that this square right here, so our final velocity is going to be equal to the square root of 4 plus 137.36. And you have to remember this is really giving us a positive and a negative value. So this final velocity can actually be equal to this minus 11.89 feet per second. And this minus sign just means it's moving in this opposite direction, which is what we would expect. But when you put this square root into a calculator, you're only going to get your positive root.